are still under subtopic 11.2, whereby the system is non-isolated, so we expect there are external force exerted to the system. Alright, we are going to use example 11.4 as our reference. However, the technical aspect will be using different way from what's given by the book. Okay, the technique is as such, whereby first and foremost, we need to draw free body diagram of all three material. So what are our three material? Our three objects given is mass number 1, hanging object, mass number 2, the block, and number 3 is a pulley. Now, the pulley, you will find that the shape is made of thin rims. So thin rims represent hollow and thin solid, thin and hollow sphere. Sorry. Okay, here it says that the spoke is jari dia, ya, has negligible mass. So you tend, they would like you to ignore it. Okay, now let's start with object number 1. Since object is supposed to be accelerating downwards, so we find that the net acceleration for number 1 would be a product of T1, the upward force tension, minus mg equivalent to negative m1a. Okay. Alright, this is our first expression. Right, now we have three expressions altogether. So our second expression comes from the block. Now according to the figure, there is no friction and only acted one single tension towards it. So away from the object as given. So this is how it looks like. And therefore, when we put it into Newton's law, we find that negative T, tension 2, okay, there will have different tension because we have one object at the center. Okay, previously pulley is not there, therefore tension equivalent. Sekarang pulley ada, jadi the tension are not similar to one another. So kita akan nampak bahawa the net acceleration adalah negative m to a. Siapa yang bertanya negatif? Sebab object move to the left. Right? So simplified kita ada expression ni. So ini kita akan labelkan sebagai our second expression. Now our third expression dia akan datang from the pulley. Now observe carefully that the direction of the T, individual T, terbalik in opposite direction. Because why? Object dia tali yang sama. Now this is the same string. So therefore its experience T1. However, T1 on pulley mestilah away from the pulley. And T2, same string as T2 tetapi direction dia away from pulley juga. Newton third law. Okay, kalau macam law sikit, okay, recall balik bahawa Newton third law kata ada dua arah tapi acted on different object. Right. So this is the one acting on the pulley. Now, this is the part where you have learned previously, whereby torque is I alpha, net torque to be precise. So you will find that T1, okay, is actually will produce you counterclockwise, and this one will produce you, here, clockwise. So this is a negative torque, and because of the negative torque, so individually it should become T1R minus T2R, and then we factorize it into here, and it's equivalent to I alpha. So something to add on to I and alpha. I is because it's a thin, hollow, solid. No, sorry, not solid, sphere. So therefore, it has the I, which is equivalent to mr squared. Number 2 alpha, go back to the linear relationship with angular. A is R alpha. So we are going to fix this. Put it as capital R according to the figure. So here it is. So we are going to replace this into here so that everything has the same constant, which is in this case, variables, which is A. What we are going to do next is, we are going to substitute the equation 1 N2 into our net torque equations, right? And T1 just now is M1G plus minus M1A. So this is T1. This is T2 and times R. So this is I mr squared, and then this is the alpha. So when we simplify, okay, we find that we can now cancel away all the R, and then let's now factorize the A. So A is negative M1C to be divided with negative M1 minus M2 minus M, where you can factorize again negative 1 M1Z over negative 1 M1 plus M2 plus M. So similar as the given answer in the book itself. Now let's revisit the idea of angular momentum. The calculation should be I times mr squared, okay, and you should find that the thing can be as well expressed by this version, I omega. How do we arrive to this conclusion? We find that V, the product of V, is equivalent to R omega. So you can see that when you simplify, it turns into a generic expression of mr squared omega. And this is very similar to this, where mr squared is I. Right, now that's one additional expression that we are going to see. So aside as writing as MVR, and recall as well that we are going to use net torque is equivalent to I alpha in the next expressions. Now let's turn to example 11.5, the seesaw. Now in this example, we are going to see there are three objects, father, daughter, and as well a seesaw. Okay, now the seesaw will make use or using the model that it's having the I equivalent to 1 over 12 ml squared, perhaps L here. Now, how do you know that we are going to use I equivalent to 1 over 12? You need to go to page 261, pause the video, go to this page, look for a thin long rod which very much resembles the seesaw, where axis of rotation is located at the center. So this is how and why we decide that I should be given or should be using this expression. Now, however, for the mass for the father and daughter, there is no model indicating as such, whereby we find that axis of rotation is outside of their body. And because of that, we are going to calculate the I individually for father and the daughter as expression mr squared, whereby the R is L over 2. Okay. Now, therefore, for question A, find an expression whereby indicating or calculating the angular momentum of the three objects together. We find that for the rods, it's 1 over 12 ml squared. for the father, mass of the father times the r squared, whereby the r is partial length, half of the length itself, and including the daughter, which is length over 2. Now, the total moment of inertia just now times with the omega. So that will give you what we call as angular momentum for the three objects. For B, find an expression, magnitude of the angular acceleration of the system when the seesaw makes an angle as given in the figure. Alright, something to observe. Yeah, when you now start talking about acceleration, means that you are talking about or relationship with the torque itself. Okay, now to look in terms of the torque, observe how my sketch changes now. That the given angle, okay, that are equivalent in one another. However, if you insist to using sine theta, it means that you must ensure that it should be 90 minus theta. That's one thing. Otherwise, you can opt using cos theta, because cos theta will give you a perpendicular product of such mg. So this is the cos, yeah, mg cos theta, perpendicular. Same goes with the daughter, so mg cos theta. So therefore, that's how you convey in terms of the force direction. So that is perpendicular with the lever arm. Where is the lever arm? This is the lever arm, yeah, right from here to here. So the blue just now indicating the axis of rotation, the lever arm. Now coming back to the story, so what will be the direction of the torque for the daughter? This is how the direction of the torque. You find that for the daughter, it's supposed to be clockwise, so it's by negative direction. For the father, it will be counterclockwise, and hence the torque is a positive value. And for that reason, you find that torque by the father is a positive and out. So it's a positive value and out. For the daughter, it's into the page, so it's a negative value clockwise, counterclockwise. Okay, and while the value itself is as given, where the R is L over 2, right? Right, if we are to isolate the whole idea, so this is the force and this is the R. And in terms of the angle, so you are using cos theta because we want F and R perpendicular with one another. Now goes the same for the daughter. Now the next step, okay, we are going to combine the two torques together, add them up, sum them up. However, you need to consider that the daughter is negative in direction, yeah, negative in direction, and that's the reason why it's minus. So factor them up, then divide by the moment of inertia. Why? Because we just recall that torque is, so since torque is I alpha, okay, and you find that torque alpha is to be divided with moment of inertia, and moment of inertia had been calculated earlier in answers A. Yeah? Right. Alright, now let us look at the last subtopic, which is isolated system. So during isolated system, you will find that net external force is 0, net torque as well is 0. Okay, net torque should as well be 0 as well. Now, therefore, the amount or total angular momentum would be the same amount, initial and final. Okay, so that's why conservation of angular momentum would be written as total would be equivalent, initial and final, or similar as this, the total angular is constant, either in magnitudes and direction. But external force and external torque should be 0. That is, system is isolated system. Okay, now coming back, the terms that change in here, change in momentum is equivalent to 0 is actually indicating that total momentum initial should be equivalent to total momentum final. So the way we tend to write it will be something like 11.1 1 just now. Right. This example shows you this dancer, okay, whereby when he spin, at the moment when he pulls his arm, okay, and leg close to his body, so overall moment of inertia would be getting smaller, and therefore, yes, angular speed would be large. And if this is the opposite side, whereby in order for him to stop, what he do is, or to slow down, okay, he just open wide his arm and leg, open outwards, okay, the arm and the leg, so that it will produce a bigger moment of inertia, and therefore his angular speed will just reduce. So in overall, for the case just now, okay, for both case just now, we can write it in this version, okay, whereby we go back to 11.21. Alright, nevertheless, this is valid for both rotation, where a fixed axis, we have a fixed axis, and whereby an axis through the center of the mass, okay, uh, as long as the axis remain fixed, okay, in directions. Therefore, to conclude what is isolated system, then it should have three things: no energy transfer, no net external force, and no net external torque. We are going to start our discussion with example 8.14, the spinning stool. In this example, you will observe the usage of conservation of angular momentum and the effect when there is no force, no torques, net torque is 0, net force is 0 as well, and therefore there is no angular acceleration. So omega, angular speed or angular velocity, would be totally dependent on how much angle covered, right, and within the time frame given. Alright, let's have a look at the question. You have the student, as in the figure, sit on a pivoted stool. That stool is free to rotate, and you have a fixed axis, and that's the reason, one of the reason why angular momentum is constant. The moment of inertia of the student originally is this much. When that student is set into rotation with his arm open, he makes one complete turn within 1.26 seconds. So what does this mean? This is the speed product. So when the question asks what is his initial angular speed, you are to make use of the idea that one turn occur in within 1.26 seconds. So how much angle covered in within one turn? It's 2 pi. So this is the theta, and this is the time taken within one rotation, 1.26 seconds. So you arrive with 4.99 rad per second. Now done with the A. Now what about B? As he rotates, he pulls the weight inward. Now pulling it inward means that there will be new moment of inertia, whereby now it reduced to 1.8. Get reduced, so change. So what will be his new angular speed? So this is the part where we will use conservation of angular momentum. Initial angular should be equivalent to the final. So look at how they substitute. If you understand properly what is I and the omega from what you have calculated earlier, then you can now calculate the new omega due to the change of the moment of inertia. Alright, for C, ignore it, it's not within the syllabus. Now let's look at another example, which is 8.15. For your information, this is very similar to our textbook, which is 11.7, very much the same. So we are going to skip 11.7, instead we are going to refer to this one. Alright, now the situation is, this is a merry-go-round that is rotating, and then all of a sudden there will be a guy, a student, somebody jump onto it. So when jumping, the moment of inertia of the whole object or of the whole merry-go-round would change. Okay, so our task is to calculate the new angular momentum. Alright, and let's start. Okay, so the merry-go-round is modeled as a disc. Okay, so since it's a disc with this mass and R, therefore the moment of inertia would be making use of half mr squared because of this. Okay, the this half mr squared. Okay, now so the m and then R, that's it. You're done with the calculation of I. So what to do with it? Since we find that it's a fixed axis, right? So afterwards, the system will undergo conservation of angular momentum. Other than that, right afterwards, okay, a student who is 60 kilogram jumping onto it, and what happened is the angular speed, okay, because they want you not to bother about the direction, because well, the direction would be conserved, remember? Okay, so it decreased too. So this is our new omega. Okay, and then afterwards as well, the student walks slowly from the edge towards the center. So you will find that we are not so much concerned about the original without the student. It's just that when jump, then you have new moment of inertia with the boy, with the student. However, the location is somewhere at the rim. Right after that, he actually that student walk towards the center. Dia bergerak menuju ke tengah. So, changing his R value. So, changing his R value akan menyebabkan I dia berubah juga. Okay, I total berubah. Okay, let's look. Okay. So there is no changing of in term of merry-go-round. So merry-go-round ni ada constant value of moment of inertia. Tetapi untuk lelaki ataupun student ni, for the student, somehow when he is at the rim, dekat rim ni, masa dia jump tu, so his MR, because axis of rotation is outside of the body, maksud dia macam ni. Dia bukan tengah-tengah badan dia. Dia di luar So axis of rotation, kita use general expression. Okay, general expression mr squared. It's m and then r at that location. Okay. So I total masa ini as in the figure. Okay. So this is the initial situation. So masa ini adalah adding these two together. Add sahaja macam normal je. Okay, mathematically. However, when he start walking towards the center, so now this is somehow his new location towards the center. Alright. So the new I will be the value of the this just now, no changes. However, his would be changing. We need to recalculate balik. Kira semula. A new calculation. So whereby inserting 0.5 just now. 0.5 R tu. Okay. And then we arrive with this one. So this is actually final angular momentum. So what we need to do next is, okay, of course, this is I and then times with the omega unknown tadi, that will be our final angular momentum. And therefore, equip it into conservation of angular momentum. Okay, masukkan, nanti you will arrive with the required final angular momentum. And look that the direction remain the same direction. Alright, let's now turn back to our textbook, example 11.6. Now, in this example, you will observe situation similar to previous. Okay, net torque is 0, net force is 0, and therefore there is no angular acceleration. When there is no angular acceleration, we expect that the calculation of omega will be purely dependent on the angle and then divide by the time. Alright, secondly, we will as well find that angular momentum would be conserved. So given situation is a star having a period of 30 days, it rotates about an axis through its center. Now the period is the time, so it's explaining time interval required for a point on a star equator to make one complete rotation, one complete revolution around the axis of rotation. Maknanya pusingan satu bulan. Macam itulah, satu pusingan. Dalam kita satu bulan. Right. So, After the stars undergoes a supernova explosion, dia dah mula berubah saiz dia. Okay, so happens to be that the radius 1 to the power of 4 kilometer, dia dah mengurang. Originally ni, ni original R initial R initial, and it collapsed into something which is much smaller. So neutron star kan 10 kilometers sahaja. So they want you to find the new period for this neutron star. Now, it's interesting to find that when we start discussing which expression of I should we use, okay? Should we use solid sphere or should it be a shell, spherical shell? Now, note that the expression can be generally written as kmr squared, where k itself could be 2 over 5 or could be 2 over 3. But nevertheless, it's still, let's say that becoming solid perhaps, okay? So if it's a solid, therefore we expect that this is 2 over 5 and therefore this is over 2 over 5 from the conservation of angular momentum. Alright, now, so writing it as such, at the same time, let's equip with the idea of omega, whereby omega is the angle divided by the time, and we find that 30 days here is the time taken to complete one rotation. So that will give you one revolution. So this is one revolution in the form of radian divided by the 30 days. However, okay, it depends. If you put it as days here and then calculate the T final, you will find that your T final would be in days. However, if you like it to be in second, then just change it into second. No problem at all. Alright. So, nevertheless, look at how they substitute. So R, we find that we can cancel out the K value just now. So regardless, so somebody who says that it should be a spherical shell, both is correct. You will end with the same answer, right? And you find as well that mass here can be cancelled out again, and it's just finally only dependence on the value of R itself, right? So as you substitute R final, which is in the kilometer, make sure that you are consistent of your units, okay? If it's kilometer, then should be divided with kilometers so that the whole idea, the unit can be cancelled out with one another. So at the end of the day, if you time with 30 days like this, you arrive with 3 times 10 to the power of negative 5 days. So this is what it meant. If you stay with 30 days, you will arrive with final answer in days as well. But let's say that you convert it into second from the very beginning, then you will arrive with second at the final answer. However, for the exam, well, they're supposed to request it properly. So state your final answer in days or state your final answer in second. Okay guys, that's it for this topic. Thank you very much.